February 7th, 1945. Yokosuka Naval Air Technical Arsenal, approximately 30 miles south of Tokyo. Commander Minoru Genda stood in the cold morning air, watching as ground crews carefully positioned a peculiar aircraft outside the testing hangar. The inverted gull wings gave it an unmistakable silhouette against the overcast sky. Bright red hinomaru roundels had been hastily painted over the American star and bar insignia, but the aircraft's origins remained obvious to anyone with eyes. This was a Chance Vought F4U Corsair, and it should not have been here. The aircraft had arrived 3 weeks earlier, transported by rail from Rabaul after capture in the Solomon Islands. Japanese recovery teams had found it nearly intact following an emergency landing on a contested airstrip, the pilot having escaped before IJN forces secured the position. Now, after hurried repairs using cannibalized parts from other wrecks and improvised solutions born of necessity, the Corsair was airworthy again. It wore Japanese markings, but it remained unmistakably American in every rivet and structural member. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Genda had flown the Mitsubishi A6M0 since its earliest operational deployment. He understood intimately what that aircraft could do, its extraordinary maneuverability in turning combat, its remarkable range that allowed strikes hundreds of miles from carrier decks, its lightweight construction that sacrificed protection for performance. He had also read the combat reports that arrived with increasing frequency from the Solomon Islands, New Guinea, and the Central Pacific. Reports that described American fighters that could absorb punishment that would destroy a Zero, that dove away from pursuing Japanese fighters with impunity, that dictated engagement terms through superior speed and power. The Corsair represented everything Japanese pilots had learned to fear. Now Genda would fly it himself, and in the process discover exactly why so many Zero pilots were not returning from combat missions against American carrier task forces. The test flight would last less than 90 minutes, but the revelations it produced would reshape Japanese understanding of what they faced in the Pacific skies. This moment represented the culmination of a desperate search for intelligence that had begun nearly 2 years earlier, when American fighters first began appearing over the Pacific that possessed capabilities Japanese planners had not anticipated. Understanding how this aircraft came to be tested at Yokosuka requires examining the evolution of American carrier fighter development and the increasingly desperate situation facing Japanese naval aviation by early 1945. The Chance Vought F4U Corsair traced its origins to February 1938, when the United States Navy Bureau of Aeronautics issued a request for proposals for a new carrier-based fighter. The requirement specified an aircraft capable of maximum speed exceeding 400 miles per hour, a ceiling above 30,000 feet, and landing speed low enough for carrier operations. These specifications pushed the boundaries of existing technology, requiring designers to extract maximum performance from available engines while maintaining the specific handling characteristics necessary for carrier landings. Chance Vaught's design team, led by Chief Engineer Rex Beisel, created a proposal centered around the most powerful engine then available for fighters, the Pratt & Whitney R2-800 double Wasp 18-cylinder radial producing 2,000 horsepower. This massive engine promised the performance Navy specifications demanded, but it created substantial design challenges. The large propeller diameter required to efficiently absorb 2,000 horsepower would necessitate either extremely long landing gear to provide propeller ground clearance or an innovative solution to the geometric problem. Beisel's team chose innovation. They designed an inverted gull wing configuration that allowed the main landing gear to be relatively short while still providing adequate propeller clearance. The wing center section angled upward from the fuselage at a pronounced dihedral, then transitioned to a conventional straight-section outboard. This distinctive configuration became the Corsair's most recognizable feature, creating a silhouette unlike any other fighter in the Pacific War. The prototype XF4U-1 made its maiden flight on May 29, 1940, with Lyman Bullard at the controls. Initial flight testing revealed exceptional performance that exceeded Navy specifications significantly. The aircraft achieved 405 miles per hour in level flight during October 1940 testing, making it the first American fighter to exceed 400 miles per hour in sustained flight. Climb rate exceeded 3,000 feet per minute. Service ceiling reached 36,900 feet. The Corsair possessed performance that promised to revolutionize carrier aviation, but exceptional performance came with challenging handling characteristics that would delay the Corsair's introduction to carrier operations for nearly 2 years. The aircraft's long nose and cockpit, positioned far aft on the fuselage, created severe visibility restrictions during carrier approach, when pilots needed to see the landing signal officer providing critical guidance. The powerful engine produced substantial torque that caused pronounced left-turning tendency during takeoff and landing, requiring constant rudder correction. Most troublingly, the wing stall characteristics proved dangerous at the slow speeds required for carrier approaches. The Corsair's stall was abrupt and violent, with little warning before one wing dropped sharply, potentially causing a spin at low altitude where recovery was impossible. The combination of poor visibility, difficult handling, and dangerous stall characteristics made the aircraft unsuitable for carrier operations until these issues could be addressed. The Navy initially rejected the Corsair for carrier deployment, instead assigning it to Marine Corps squadrons operating from land bases where the handling challenges posed less risk. Marine Corps Squadron VMF 124 received the first operational F4U Corsairs in October 1942 at Camp Kearney, California. Pilots transitioning from earlier fighters like the Grumman F4F Wildcat found the Corsair's performance thrilling but its handling demanding. The aircraft required constant attention during all phases of flight, particularly during takeoff and landing, where the powerful engine and challenging visibility demanded experienced piloting. But once mastered, the Corsair provided performance that exceeded anything Japanese fighters could match in the categories that mattered most for Pacific combat. The first Marine Corsair squadron to see combat was VMF 124, which deployed to Guadalcanal in February 1943 under the command of Major William Giese. The squadron began flying combat missions on February 14, 1943, immediately demonstrating the Corsair's superiority over Japanese fighters in speed, climb rate, firepower, and structural strength. Japanese Zero pilots attempting to engage Corsairs discovered they could neither catch the American fighters in level flight nor pursue them in dives where the Corsair's superior speed and structural strength allowed escape. Combat results vindicated the Corsair's performance advantages despite its challenging handling. Marine squadrons flying Corsairs compiled remarkable kill ratios against Japanese aircraft, with some squadrons achieving better than 10-to-1 ratios. The aircraft could absorb battle damage that would destroy lighter Japanese fighters and still return to base. Its 650 caliber machine guns delivered devastating firepower in concentrated bursts, armor protection and self-sealing. Fuel tanks kept pilots alive through hits that would have proven fatal in less robust aircraft. By mid-1943, the Corsair had established itself as one of the premier fighters in the Pacific, though still operating exclusively from land bases due to unresolved carrier landing problems. Marine pilots developed tactics that exploited the Corsair's strengths while avoiding situations that played to Zero advantages. High-speed slashing attacks replaced turning dogfights. Diving escapes became standard procedure when outnumbered or surprised. Altitude advantage was maintained religiously, allowing Corsair pilots to control engagement, timing, and geometry. Japanese intelligence services tracked these developments through combat reports and interrogation of captured American pilots. They understood that American fighters possessed superior speed and diving performance, but understanding these facts intellectually differed fundamentally from experiencing them directly through testing a captured aircraft. The Japanese Navy's technical services had captured various American aircraft during the war's early phases, but most were older types that did not represent current American capabilities. The capture of relatively intact modern fighters like the Corsair remained rare because American pilots typically destroyed damaged aircraft rather than allowing them to fall into enemy hands intact. When recovery proved impossible, standard procedure called for setting thermite grenades to destroy critical components and render the aircraft unusable. Japanese forces occasionally recovered wrecks, but these typically sustained damage too severe for meaningful testing. The Corsair that arrived at Yokosuka in January 1945 represented a rare intelligence opportunity. The aircraft had made an emergency landing on a contested airstrip during fighting in the Solomon Islands. The pilot, low on fuel and unable to reach friendly territory, chose to land rather than bail out over water or hostile jungle. He successfully evacuated before Japanese forces reached the aircraft, but he had insufficient time to properly destroy it. Japanese recovery teams found the Corsair with repairable damage, primarily to the landing gear and propeller from the rough field landing. Transportation to Japan required careful planning and substantial resources that were increasingly scarce by early 1945. The Corsair was partially disassembled and shipped by transport vessel through waters increasingly dominated by American submarines. The journey took weeks, with the transport making frequent course changes and hiding in coastal anchorages during daylight to avoid American air patrols. That the aircraft reached Japan intact testified to the importance Japanese naval authorities placed on examining modern American equipment. Yokosuka Naval Air Technical Arsenal served as the primary Japanese Navy facility for aircraft testing, development, and technical intelligence. The facility employed experienced test pilots, skilled engineers, and technicians capable of evaluating foreign aircraft despite lacking technical manuals or original spare parts. Previous captures had been examined there, including early war American types like the Brewster Buffalo and Grumman Wildcat, providing Japanese engineers with understanding of American design philosophy and manufacturing techniques. But the Corsair represented a quantum leap beyond these earlier captures. This was a current production fighter incorporating the latest American technology and design thinking. Examining it would reveal how far American aviation had progressed since Pearl Harbor and provide concrete evidence of the challenges Japanese pilots faced in combat against American carrier task forces. The repair process consumed 3 weeks of intensive work by skilled technicians operating under severe resource constraints. Replacement parts did not exist, requiring fabrication and components using available materials. The damaged landing gear was straightened and reinforced using steel salvaged from other wrecks. The propeller, which had bent tips from the rough landing, was carefully dressed and balanced. The Pratt & Whitney R2800 engine underwent complete inspection, with suspicious components replaced using parts cannibalized from other captured American engines held in storage. Japanese technicians marveled at the quality of materials and manufacturing evident throughout the aircraft. The aluminum alloys used in airframe construction exceeded Japanese material quality significantly, combining high strength with relatively low weight. Rivet work was precise and consistent. Welding quality on steel components showed exceptional skill. Control cables were properly tensioned and routed efficiently. The entire aircraft demonstrated manufacturing sophistication that reflected American industrial capabilities and quality control processes. The cockpit instrumentation impressed Japanese engineers familiar with increasingly crude gauges and instruments in late-war Japanese aircraft. American instruments remained clearly marked with easy-to-read faces and smooth operation. The fuel system included features not found in Japanese fighters, particularly the sophisticated fuel management system that allowed pilots to draw from multiple tanks in proper sequence. The hydraulic system operated flaps, landing gear, and cowl flaps reliably using components manufactured to tight tolerances. Most remarkably, the armament installation demonstrated American firepower philosophy clearly. 6 Browning 50 caliber M2 machine guns, 3 per wing, provided concentrated firepower that dramatically exceeded the typical Japanese fighter armament. Each gun received 400 rounds of ammunition for total capacity of 2,400 rounds. This massive ammunition load allowed sustained firing during multiple engagements without concern for running out during extended missions. Japanese fighters typically mounted 2 rifle-caliber machine guns and 2 20mm cannons with limited ammunition capacity. The Corsair's armament represented entirely different philosophy, trading the cannon's explosive power for sustained volume of fire from the heavy 50-caliber guns. Combat experience had proven the 50-caliber armament devastatingly effective against Japanese aircraft, whose light construction offered minimal protection against the heavy bullets. By early February, the Corsair was declared ready for flight testing. Commander Genda received orders to conduct the initial evaluation flights and prepare a comprehensive report on the aircraft's capabilities, handling characteristics, and tactical implications. Genda brought substantial experience to this assignment, having flown numerous Japanese types and participated in planning the Pearl Harbor operation. He understood carrier aviation doctrine thoroughly and possessed the skill necessary to safely evaluate an unfamiliar aircraft with potentially dangerous characteristics. The morning of February 7th dawned cold and overcast, typical weather for Tokyo area in winter. Ground crews towed the Corsair from its hangar to the flight line, where final pre-flight inspection revealed no obvious problems. Genda walked around the aircraft slowly, examining it from all angles and noting details that photographs and reports could not convey. The sheer size impressed him immediately. The Corsair was substantially larger than the Zero, with wingspan of 41 feet and length exceeding 33 feet. Empty weight exceeded 8,000 pounds, nearly double the Zero's empty weight. The inverted gull wing created distinctive geometry that looked almost awkward on the ground but promised aerodynamic advantages in flight. The large propeller, measuring over 13 feet in diameter, required the unusual wing configuration to provide ground clearance with acceptable landing gear length. Genda climbed onto the wing and into the cockpit, which sat high on the fuselage and far aft compared to Japanese fighters. Visibility forward was severely restricted by the long nose and large engine cowling. He could barely see over the nose while sitting in the cockpit, understanding immediately why American pilots found carrier landings challenging in this aircraft. The instrument panel displayed systematic organization with clearly labeled gauges grouped by function. Engine instruments occupied the left side of the panel. Flight instruments centered directly before the pilot. Fuel and hydraulic system gauges filled the right side. Everything was marked in English, which Genda read adequately, though not fluently. The control stick felt substantial and well-made, its grip worn smooth by previous use. Rudder pedals required adjustment to accommodate his shorter legs, a common issue for Japanese pilots flying captured American aircraft designed for taller aviators. Ground crew started the massive R2800 engine, which caught on the third blade and settled into a powerful idle that vibrated the entire airframe. Exhaust from the 18 cylinders created a distinctive deep rumble unlike any Japanese engine. Genda advanced the throttle slightly, feeling the aircraft strain against the wheel chocks as 2,000 horsepower pulled against the brakes. The power available exceeded anything he had experienced in Japanese fighters, promising performance that would either thrill or terrify, depending on his ability to control it. He released the brakes and the Corsair rolled forward, its tail wheel steering responding to rudder pedal inputs. Taxiing required constant attention as the powerful engine and heavy weight made the aircraft want to weather vane in the slightest crosswind. Visibility during taxi was poor, requiring S-turns to see ahead around the long nose. Genda understood why American pilots considered the Corsair challenging even before flight began. Simply moving the aircraft on the ground demanded more attention than flying some Japanese trainers. Reaching the runway threshold, Genda completed final checks and prepared for takeoff. He aligned the aircraft carefully on the runway centerline, set the tailwheel lock, and smoothly advanced the throttle to full power. The acceleration was immediate and dramatic. The Corsair surged forward with authority, quickly building speed as the massive propeller pulled it down the runway. Torque from the powerful engine tried to swing the nose left, requiring substantial right rudder pressure to maintain directional control. The tail lifted after brief roll, improving forward visibility significantly. Airspeed increased rapidly through 50 knots. 60, 70. At approximately 85 knots, Genda eased back on the stick, and the Corsair lifted smoothly into the air, climbing away from Yokosuka with power and authority that exceeded his expectations dramatically. The climb rate shocked him immediately. The Corsair ascended at over 3,000 feet per minute, nearly double the Zero's climb rate at sea level. Genda watched the altimeter unwind rapidly as the aircraft clawed upward through the cold February air. The engine ran smoothly at climb power, showing no signs of the overheating problems that plagued some Japanese engines when pushed hard. Oil pressure and temperature remained solidly in normal ranges. Cylinder head temperatures stayed comfortably below maximum limits. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 5,000 feet, Genda leveled off temporarily to assess basic handling characteristics before continuing his evaluation. He performed gentle turns left and right, feeling how the aircraft responded to control inputs. The ailerons were heavy but effective, requiring more physical force than the Zero's feather-light controls, but providing positive response with no sloppiness or delay. The elevator forces were well harmonized with the ailerons, creating balanced handling that made coordinated flight natural. What struck him most forcefully was the Corsair's stability. The Zero was a nimble, sensitive aircraft that responded instantly to pilot inputs, but required constant attention to maintain steady flight. The Corsair felt solid and planted, maintaining altitude and heading with minimal corrections. It was an aircraft designed to fly long missions over ocean distances, where pilot fatigue became a critical factor. This stability would reduce workload significantly during extended combat patrols. Genda continued climbing to 15,000 feet, monitoring the engine carefully for any signs of distress at altitude. Japanese engines frequently suffered declining performance above 10,000 feet as their single-stage superchargers struggled to compress the thinning air adequately. The Corsair's R2800, equipped with a two-stage supercharger, showed no such weakness. Power remained strong throughout the climb. Engine gauges indicated the supercharger was functioning properly, maintaining manifold pressure as altitude increased. At 15,000 feet, Genda began performance testing in earnest. He accelerated to maximum speed, advancing throttle and propeller controls to war emergency power settings. The Corsair surged forward with authority, accelerating smoothly through 300 miles per hour, 350, 400. The airspeed indicator finally stabilized at approximately 417 miles per hour in level flight at 15,000 feet. This exceeded the Zero's maximum speed by over 60 miles per hour, a margin so substantial it fundamentally altered combat dynamics. The tactical implications crystallized in Genda's mind with uncomfortable clarity. A Zero pilot engaging a Corsair could not run away. If the combat situation turned unfavorable, if the Zero pilot became wounded or his aircraft damaged, if ammunition ran low or fuel state became critical, escape was impossible. The Corsair could chase down any Zero in level flight effortlessly. This single fact inverted the tactical equation that had favored Japanese pilots early in the war. Genda tested high-speed handling, performing rolling maneuvers and turns at 400 miles per hour. The controls remained responsive and effective even at these speeds, where the Zero's fabric-covered ailerons would balloon and lock up. The Corsair's metal-skinned control surfaces maintained authority throughout the speed range, allowing aggressive maneuvering at velocities where Japanese fighters became sluggish and unresponsive. He initiated a dive from 15,000 feet, pulling the nose down smoothly and letting the Corsair accelerate under gravity and engine power. The airspeed increased rapidly, passing 450 miles per hour, 475, 500. The aircraft remained stable and controllable throughout, with no buffeting, vibration, or tendency toward control reversal. Genda pulled firmly on the stick to level out at 5,000 feet, feeling significant G-forces press him into the seat as the aircraft pulled through the bottom of the dive. The structure handled the stress without complaint. No creaking, groaning, or flexing that would indicate overstress. The Corsair was built substantially, engineered with large safety margins that allowed violent maneuvering without risking structural failure. Japanese fighters, designed to minimum structural requirements to save weight, could not sustain such punishment without risk of catastrophic failure. Combat reports of Zeros breaking up in high-speed dives suddenly made perfect sense to Genda. American pilots exploited superior diving performance, knowing Japanese fighters could not follow safely. Climbing back to altitude, Genda tested the Corsair's turning performance, the area where Japanese pilots expected their fighters to retain advantage. He established a level turn at moderate speed, gradually increasing bank angle and back pressure on the stick. The Corsair turned steadily with considerable G-force building as the turn tightened. The aircraft could complete a full circle in approximately 22 seconds at optimal speed and bank angle. This turn performance was respectable, but clearly inferior to the Zero's remarkable 18-second turn time. In a sustained turning fight at low to moderate speeds, the Zero would gradually gain angular advantage, eventually positioning behind the Corsair for a firing solution. This represented the one area where Japanese fighters retained clear superiority, the one tactical situation where engagement should be sought rather than avoided. But Genda immediately recognized the limited value of this advantage. The Corsair pilot who allowed himself to be trapped in a sustained turning engagement at low speed was either incompetent or desperately unlucky. Properly flown, the Corsair would never accept such combat geometry. American pilots could dictate engagement range and timing through superior speed. They could climb above Japanese fighters and attack from altitude with speed advantage. They could dive away from unfavorable situations faster than Zeros could follow. The turning advantage that had dominated early war combat became increasingly irrelevant as American fighters exploited performance advantages in speed, climb rate, dive capability, and structural strength. Japanese tactical doctrine, built around turning combat where Zero advantages dominated, had become obsolete against aircraft like the Corsair that fought differently and more effectively. Genda tested stall characteristics next, an area of known concern from intelligence reports about Corsair carrier operations. He reduced power and raised the nose gradually, bleeding off airspeed until the aircraft approached stall. At approximately 92 knots with power at idle and nose high, the left wing dropped sharply without warning. The aircraft snapped into the beginning of a spin entry before Genda recovered with opposite rudder and forward stick. He repeated the test several times, approaching the stall from different configurations and power settings. The stall behavior remained consistently abrupt and asymmetric, with little buffet or warning before one wing dropped sharply. This explained why the U.S. Navy had initially rejected the Corsair for carrier operations. Landing approaches required slow flight near stall speed with precise control. An abrupt stall during final approach at low altitude would be fatal with insufficient height for recovery. But American pilots had learned to manage this characteristic through proper technique and training. Maintaining adequate airspeed throughout the approach prevented stall encounters. The dangerous stall behavior only manifested during slow flight near minimum speed, a condition that could be avoided through disciplined airspeed management. Japanese pilots would need similar training if they attempted to operate captured Corsairs, though Genda recognized this was purely academic speculation given Japan's deteriorating situation. After nearly 90 minutes of comprehensive testing, Genda returned to Yokosuka, setting up for landing with considerable caution given the visibility restrictions and known handling challenges. The approach required careful speed control, maintaining 110 knots until short final, then reducing smoothly to approximately 95 knots over the threshold. Forward visibility was terrible with the long nose blocking the runway from view. Genda flew the approach using peripheral vision and practiced judgment about the aircraft's attitude and position. The touchdown was firm but controlled, the robust landing gear absorbing the impact without complaint. Genda applied brakes carefully, conscious that the powerful aircraft with its high landing speed required substantial runway length for stopping. The Corsair rolled out smoothly and turned off the runway, its test flight complete. Genda taxied back to the hangar, his mind already organizing observations into the comprehensive report that would be required. Ground crews swarmed the aircraft immediately after engine shutdown, conducting post-flight inspection and servicing. Genda climbed down from the cockpit and walked slowly around the Corsair one more time, seeing it now with the understanding that came from flying rather than just observing. This was a formidable aircraft, designed by competent engineers, built with quality materials and skilled manufacturing, and capable of performance that exceeded Japanese fighters decisively in the categories that mattered most for Pacific combat. Over the following week, Genda flew the Corsair 4 additional times, each flight exploring specific aspects of performance and handling in greater detail. He tested acceleration at various altitudes, measuring how quickly the aircraft could convert throttle input into speed increase. He evaluated fuel consumption at different power settings, calculating range and endurance under various mission profiles. He performed mock combat maneuvers against imaginary opponents, evaluating how the Corsair would fight against zero tactics. He tested the 650 caliber machine guns, firing into target panels to assess the armament's effectiveness. The concentrated firepower devastated the test targets with short bursts. Each gun fired approximately 800 rounds per minute. With all 6 guns firing simultaneously, the Corsair delivered approximately 4,800 rounds per minute, nearly 80 rounds per second of heavy 50 caliber ammunition. This firepower exceeded Japanese fighter armament dramatically in sustained firing capacity. The 50 caliber bullets, each weighing approximately 730 grains and traveling at approximately 2,800 feet per second, delivered tremendous kinetic energy to targets. Combat films captured by American aircraft showed these projectiles literally tearing apart Japanese aircraft, punching through thin aluminum skin, severing control cables, destroying engines, and setting fire to unprotected fuel tanks. The Zero's light construction, designed to minimize weight for maximum performance and range, offered virtually no protection against such punishment. Genda's subsequent test flights confirmed and refined his initial impressions. The Corsair possessed overwhelming advantages in speed, climb rate, dive performance, firepower, and structural strength. It sacrificed some maneuverability for these attributes, particularly in sustained turning at moderate speeds, but this trade-off clearly favored the American design philosophy for the type of combat that actually occurred in the Pacific Theater by 1944 and 1945. Japanese engineers at Yokosuka conducted their own detailed technical examination of the Corsair, while Genda flew his test program. They measured and documented every aspect of the aircraft's construction, creating detailed drawings of structural components, analyzing material composition, and evaluating manufacturing techniques. Their findings painted a sobering picture of American industrial and engineering capabilities. The quality of aluminum alloys used throughout the airframe exceeded Japanese metallurgical capabilities significantly. American alloys combined high strength with good workability and corrosion resistance, allowing designers to create structures that were both strong and relatively lightweight. Japanese aluminum production suffered from inconsistent quality and limited access to alloying elements, resulting in materials that were either strong but brittle or ductile but weak. Manufacturing precision, evident throughout the Corsair, demonstrated sophisticated production control. Rivet holes were precisely drilled and properly countersunk. Rivets were uniformly installed with consistent shop heads. Welding on steel components showed excellent penetration and minimal defects. Tolerances on machined parts were tight and consistent. The entire aircraft reflected manufacturing capabilities that Japanese industry could not match, particularly under the strategic bombing and resource constraints of late 1944 and early 1945. The engine represented perhaps the most impressive technological achievement, the Pratt & Whitney R2-800 double wasp, displacing 2,804 cubic inches across 18 cylinders arranged in 2 rows, produced 2,000 horsepower at 2,700 RPM using 56 inches of manifold pressure. This power output significantly exceeded any Japanese radial engine in operational service. The 2-stage supercharger system, with its intercooler between stages, maintained power output at high altitudes, where Japanese single-stage superchargers lost effectiveness dramatically. Japanese engineers carefully examined the supercharger installation, noting the sophisticated ducting, the efficient intercooler design, and the automatic controls that managed the system without requiring constant pilot attention. Replicating such technology would require years of development work and manufacturing capabilities Japan no longer possessed. The propeller, a 4-bladed Hamilton Standard hydromatic constant-speed unit with diameter of 13 feet 4 inches, represented another area of American technological leadership. The mechanism that automatically adjusted blade pitch to maintain optimal propeller RPM, regardless of flight conditions, operated smoothly and reliably throughout Genda's test flights. Japanese constant-speed propellers suffered from reliability problems and required frequent maintenance. The American design demonstrated superior engineering and manufacturing quality. Japanese engineers examined the hydraulic system that operated landing gear, flaps, and cowl flaps with professional interest. The system used quality components manufactured to precise tolerances, ensuring reliable operation under the demanding conditions of carrier aviation. Hydraulic lines were properly routed and secured. Actuators operated smoothly without leakage. The entire system reflected careful design and quality manufacturing. The self-sealing fuel tanks particularly impressed Japanese engineers. Multiple rubber layers and chemical compounds reacted with fuel to automatically seal bullet holes, preventing or minimizing fuel loss and reducing fire risk. Japanese fighters lacked this protection entirely, relying instead on superior maneuverability to avoid being hit. Combat experience proved this philosophy fatally flawed. American pilots with adequate ammunition could eventually hit maneuvering targets, and a single hit to an unprotected fuel tank often proved catastrophic. Armor protection for the pilot, another feature absent from Japanese fighters, was evident throughout the Corsair's cockpit area. Steel armor plate behind the pilot's seat would stop rifle-caliber bullets and fragments. The windscreen incorporated bulletproof glass capable of resisting multiple hits. Head armor protected against attacks from above and behind. This protection added weight that reduced performance marginally, but dramatically improved pilot survival rates, allowing experienced aviators to fly multiple combat tours rather than dying on early missions. The accumulated evidence from both flight testing and technical examination forced an uncomfortable conclusion. The Corsair represented a fundamentally superior fighter design for the kind of combat that characterized the Pacific War by 1945. It incorporated sophisticated technology in the engine, propeller, and systems. It was built with quality materials and precision manufacturing. It protected the pilot and vital components against battle damage. It delivered overwhelming firepower through 6 heavy machine guns. Most importantly, it could dictate combat conditions through superior speed, climb rate, and dive performance, engaging when advantageous and disengaging when threatened. Japanese fighters could no longer force combat on unwilling opponents. This represented a complete reversal from early war conditions when Zero pilots controlled engagement timing and geometry against slower, less capable Allied fighters. Genda's final report, submitted to the Naval Air Technical Arsenal on February 21, 1945, synthesized his observations into a comprehensive assessment that made grim reading for Japanese naval aviation authorities. He documented the Corsair's substantial performance advantages in every category except sustained turning at moderate speeds. He explained how American pilots exploited these advantages through tactics that avoided Japanese strengths while maximizing their own aircraft's capabilities. He noted that Japanese pilots, trained primarily in dogfighting techniques that emphasized turning combat, were poorly prepared for opponents who refused to turn and instead fought using energy tactics, vertical maneuvers, and hit-and-run attacks. Most critically, Genda stated explicitly that Japanese fighters could not compete with aircraft like the Corsair, given current technology and industrial capabilities. The performance gap was too large to close through tactical innovation or improved pilot training alone. Recommendations in Genda's report reflected the desperate reality of Japan's strategic situation by early 1945. He suggested Japanese fighters should avoid engaging Corsairs and other advanced American fighters whenever possible, instead focusing on attacking bombers and transport aircraft that were less capable of defending themselves. He recommended that when combat with American fighters was unavoidable, Japanese pilots should seek to force low-speed turning, engagements where zero maneuverability provided some advantage, while avoiding high-speed combat where American fighters dominated completely. He advocated for improved pilot training, emphasizing energy management and defensive tactics, though he acknowledged that fuel shortages and loss of training facilities made this recommendation largely impractical. He suggested accelerating development of Japanese fighters with better high-altitude performance and higher speed, though he recognized that industrial constraints and material shortages would prevent such aircraft from entering service in meaningful numbers before war's end. The report circulated through Japanese Naval Aviation Command structure, reaching senior officers who understood its implications fully. Japan had lost the technological and industrial race decisively. American fighters combined superior performance with overwhelming numerical advantage and better trained pilots. Japanese forces could no longer contest air superiority over most of the Pacific. The best Japanese pilots in the best Japanese aircraft were being systematically destroyed by American forces that grew stronger daily, while Japanese capabilities declined. Other Japanese pilots received opportunities to fly the captured Corsair during March 1945, as the aircraft remained at Yokosuka for continued testing and demonstration. Each pilot who flew it returned with similar observations. The aircraft was fast, powerful, well-built, and possessed performance that Japanese fighters could not match. Several experienced pilots noted that had Japan possessed such aircraft in significant numbers, the Pacific War's outcome might have been substantially different. But such speculation was pointless. Japan lacked the industrial capacity, material resources, technological sophistication, and manufacturing capabilities to produce fighters comparable to the Corsair. American industry produced approximately 12,500 Corsairs during the war years, along with thousands of other advanced fighters like the P-51 Mustang and P-47 Thunderbolt. Japanese production of all fighter types combined totaled approximately 30,000 aircraft during the entire war, and quality declined significantly in late war production as materials became scarce and manufacturing conditions deteriorated. The Corsair that Genda tested represented not just a single aircraft, but an entire industrial and technological system that Japan could not replicate. Behind every Corsair stood American factories with sophisticated machine tools and skilled workers. American aluminum refineries producing high-quality alloys. American engine plants manufacturing precise components to tight tolerances. American research facilities developing advanced technologies. American training programs producing skilled pilots in large numbers. Japan possessed none of these advantages by early 1945. Combat statistics from the final year of the Pacific War reflected these fundamental imbalances. Marine and Navy Corsair squadrons compiled extraordinary kill ratios against Japanese aircraft, with some units achieving better than 10-to-1 ratios. Japanese losses included both aircraft and irreplaceable experienced pilots. American losses were quickly replaced by vast training pipelines that produced thousands of new aviators monthly and industrial production that delivered hundreds of new aircraft weekly. The captured Corsair's fate remains uncertain in historical records. Some sources suggest it was destroyed during American bombing raids against Tokyo area in March 1945, when B-29 Superfortress strikes devastated Japanese urban and industrial areas. Other accounts indicate it may have survived until war's end and was scrapped afterward during occupation. The specific aircraft's ultimate disposition matters less than the knowledge it provided Japanese engineers and pilots about the formidable capabilities of American fighters. That knowledge confirmed what many Japanese aviators already suspected from hard-won combat experience. They faced opponents with superior equipment, overwhelming numbers, better logistics, more thorough training, and strategic advantages that could not be overcome through courage, skill, or tactical innovation alone. Understanding why Zero pilots were dying required no complex analysis after flying the Corsair. American fighters were simply better in the ways that mattered most for Pacific combat. The Zero had been a revelation when it first appeared over China in 1940 and at Pearl Harbor in 1941, outperforming every opponent it encountered through superior maneuverability, remarkable range, and adequate firepower. But aircraft development had not stopped in 1940. American designers learned from early defeats, identified the performance characteristics most critical for Pacific combat, and created fighters optimized for those requirements. The Corsair embodied this evolution. It sacrificed some maneuverability to gain speed. It accepted higher weight to incorporate armor protection and self-sealing tanks. It used a larger, heavier engine to achieve better climb rate and high-altitude performance. It mounted more guns, with more ammunition to deliver sustained firepower. Every design decision reflected lessons learned from combat experience and a sophisticated understanding of what actually determined victory in aerial combat. Japanese design philosophy, shaped by successful early war experience, emphasized characteristics that had proven effective against weaker opponents but became liabilities against aircraft like the Corsair. Lightweight and high maneuverability mattered less when opponents refused to dogfight and instead used superior speed to control engagement conditions. Long range remained valuable but couldn't compensate for inability to survive combat against better protected opponents. Adequate firepower proved insufficient against robust American aircraft that absorbed hits and kept fighting. By the time Japanese engineers tested the captured Corsair and understood these realities fully, the strategic situation had deteriorated beyond recovery. American forces controlled most of the Pacific, steadily advancing toward Japan itself. Japanese industry struggled to maintain even reduced production rates under intense bombing. Fuel shortages, grounded training programs, and limited operational sortie rates. Experienced pilots were being lost faster than replacements could be trained even to minimal proficiency levels. The knowledge gained from testing the Corsair provided no path to victory or even to achieving favorable combat exchange rates. It simply confirmed the magnitude of disadvantages Japanese forces faced. Understanding your opponent's superiority offers little practical benefit when you lack the resources, technology, and industrial capacity to close the performance gap or the strategic position to avoid combat entirely. Genda survived the war and continued serving in Japan's post-war self-defense forces, eventually reaching the rank of general. He rarely discussed his experience flying the captured Corsair in later years, perhaps because the memory represented Japan's decline from early war dominance to late war desperation. The test flight that revealed so clearly why 0 pilots were dying offered no solutions, only confirmation of an inevitable outcome determined by industrial and technological factors beyond Japanese control. The broader lesson from the captured Corsair testing extends beyond World War II specifics to fundamental questions about technological competition and industrial capacity in modern warfare. Superior equipment matters enormously when performance gaps are substantial. Training and tactics can compensate for modest disadvantages, but cannot overcome fundamental capability shortfalls when opponents exploit the advantages systematically. Industrial production capacity determines how quickly losses can be replaced and how rapidly forces can be expanded. American victory in the Pacific resulted from multiple reinforcing advantages that proved overwhelming in combination. Superior industrial capacity produced more aircraft, ships, and weapons. Better access to strategic materials enabled higher quality manufacturing. More sophisticated technology provided performance advantages in critical areas. More thorough training prepared personnel effectively for combat conditions. Superior logistics sustained operations across vast ocean distances. Better intelligence and code breaking provided strategic and tactical advantages. The captured Corsair represented one visible manifestation of these broader advantages. Japanese engineers who examined it thoroughly understood they were seeing evidence of American industrial and technological capabilities that Japan could not match. Japanese pilots who flew it understood they faced opponents with better equipment that they could neither match nor effectively counter given available resources and technology. This knowledge, acquired through careful testing and professional analysis, provided no comfort and offered no solutions to Japan's deteriorating strategic position. The F4U Corsair continued serving in American forces long after World War II ended, seeing extensive combat during the Korean War, where its ground attack capabilities proved particularly valuable. The type remained in production until 1952, with total production reaching 12,571 aircraft from multiple manufacturers. Many examples survived into the jet age, operating from smaller carriers where their lower landing speeds offered advantages over early jets. The Corsair's combat record speaks clearly to its capabilities. The type was credited with destroying over 2,100 Japanese aircraft in aerial combat while losing only 189 Corsairs to enemy aircraft, producing an overall kill ratio exceeding 11-1. Some squadrons achieved dramatically better ratios, with Marine Fighting Squadron 214, the famous Black Sheep Squadron led by Gregory Boyington, compiling 97 aerial victories against minimal losses. These statistics reflected the combination of aircraft performance advantages that Genda discovered during his test flights and the tactical doctrines American pilots employed to exploit those advantages. Speed allowed dictating engagement conditions. Climb rate enabled altitude advantage. Dive performance provided escape options. Structural strength permitted violent maneuvering. Firepower destroyed targets quickly. Armor and self-sealing tanks improved survival rates. Every advantage reinforced others, creating overwhelming combat effectiveness against opponents with inferior equipment. Japanese Zero pilots who survived the war and wrote memoirs or gave interviews frequently mentioned the Corsair as one of the most feared American fighters. They described the distinctive inverted gull wing profile that meant danger, the powerful engine note that signaled superior performance, and the devastating firepower that could destroy a Zero with a single well-aimed burst. They acknowledged that by war's end, engaging Corsairs meant accepting heavy losses with minimal chances of success. Understanding why Zero pilots were dying required no complex analysis after Japanese engineers tested a captured Corsair. The American fighter was simply better in nearly every category that mattered for Pacific combat. It was faster, allowing it to catch fleeing Zeros or escape from unfavorable situations. It climbed better, enabling altitude advantage for diving attacks. It dove better, providing both attack capability and escape option. It was tougher, surviving battle damage that would destroy lighter Japanese fighters. It hit harder, mounting more guns with more ammunition. The only area where the Zero retained clear advantage was sustained, turning at moderate speeds, and this advantage became increasingly irrelevant as American pilots refused to fight in the turning combat regime where Japanese aircraft excelled. Proper tactics exploited American aircraft strengths while avoiding situations that favored Japanese advantages. The result was systematic destruction of Japanese naval aviation through attrition it could not sustain. The captured Corsair tested at Yokosuka in February 1945 revealed these uncomfortable truths to Japanese engineers and pilots, confirming through direct experience what combat reports had been indicating for months. American fighters had surpassed Japanese designs decisively. The technological and industrial competition had been lost. No amount of courage, skill, or tactical innovation could compensate for fundamental performance disadvantages of the magnitude the Corsair represented. This knowledge arrived too late to change anything about Japan's strategic situation or the Pacific War's outcome. By February 1945, American forces had captured the Philippines. Bombers were striking Japanese cities with impunity. Submarines had strangled merchant shipping, and invasion of Japan itself loomed on the horizon. Understanding why Zero pilots were dying offered no path to preventing those deaths or reversing the deteriorating military situation. The story of Japanese engineers testing a captured Corsair represents a moment of professional reckoning when comfortable assumptions about relative capabilities confronted undeniable physical evidence of American technological and industrial superiority. The flight test data, technical examinations, and professional assessments all pointed to the same conclusion. Japan had lost the fighter development race decisively, and the consequences played out daily in the skies over the Pacific, where Zero pilots faced increasingly impossible odds against superior opponents. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.